Hello, my name is Zheng Chen from Indiana University Bloomington. Our research is about to construct navigable space from sparse and noisy point clouds. The problem is challenging in many scenarios where only low-quality sensors are available due to the constraints of sensor costs and dimensions. In this case, the sensed point cloud might have high irregularities, such as large noise on point position and high variation on point density. Here, we show an example of irregular point cloud obtained from a sparse virus line. One example of irregularity can be seen by comparing the blue boxes and orange boxes, where different densities of point cloud are presented. Motivated by previous described challenges, we propose our goal as to construct navigable space that excludes all obstacle points for real-time navigation. We achieve this goal by designing a framework which consists of 4 major parts. Since reconstructing the whole obstacle space might be too expensive, our fundamental part is a convex hull inflation module that conservatively extracts navigable space within the ground truth navigable space by green convex hulls, as shown in the below figure. The second part is a point cloud processing module, which reorganizes the point cloud by leveraging the extracted convex hull such that the processed point cloud is more smooth and can be further utilized in motion planning. The third part is a local navigation planning module, which finds collision-free path for the robot by stacking and examining convex hulls in real time. The last part is a new geometric metric for evaluating the volume extraction performance. Convex hulls inflation module iteratively looks for a sequence of polyhedron with maximum inscribed ellipsoids using quadratic programming and semi-definite programming. An illustration of the inflation process in 2D case is shown, and it comes from the reference paper. In 3D case, by representing an ellipsoid as an image of a unit ball and a polyhedron as a set of linear inequalities, we can formulate the problem as an optimization problem like this. Solving the problem can give us convex hulls as shown in the rightmost pictures, where the color points are the obstacle points. Point cloud processing module consists of 2 parts, one of which is point projection, while another one is point regulation. The module takes seed points, obstacle points, and convex hulls as inputs, and outputs the reorganized point cloud. The green blocks represent functions in point cloud library, while red blocks are functions proposed in this work. Points projection is to project original points onto the surface of extracted convex hulls, while point culling is to cull those projected points falling inside any convex hulls by leveraging the convexity of the hulls. We also show one example of a regulated point cloud using our proposed method in the red pictures. To navigate the robot in the constructed navigable space, we adopt a receding horizon planning scheme which consists of a local planning horizon and also a short execution horizon. We build a discrete site of candidate navigation points in camera's field of view. The projection of those candidate points on image plane are marked as blue crossings in the rightmost picture. Each candidate point carries a possibility of being selected as a seed point for a convex hull. By examining each candidate point's safety score, which is proportional to the maximum volume of a convex hull that can grow at the candidate point. Finally, the path will be formed by a set of candidate points which have the maximum sum of the safety scores. To quantitatively evaluate the navigable space constructed, we need to compare the valid volume of the convex hulls with the volume of the ground truth free space. However, the computation of the valid volume is not trivial, since each convex hull may overlap with the neighboring one, especially if the seed points are close to each other. To tackle this problem, we leverage the inclusion-exclusion principle and propose a navigable space calculation algorithm called forward-looking union volume computation. In experimental section, we first show a series of overlapping convex halls in a simulated environment and the intersections of those convex halls. To quantitatively evaluate the volume extraction performance of our proposed method and baseline method, which are based on sphere representation, we use our newly proposed forward-looking union volume computation algorithm to compute the pure volume of extracted free space. By examining the volume ratio with different parameter values, we can find our proposed method significantly outperform the baseline method. To fully validate the effectiveness of our proposed method, we also compare the navigable volume for each seed point for different methods, and we can still observe the advantage of our proposed method over baseline methods. We also test our method on a public dataset, KD5 sequence, and in a manually built structured environment. Here we show the construction results in both cases. We also care about the time performance of our proposed method, and we collect data of our method for the real build environment indicated. The table 1 here shows the size of the inputs to our proposed method, and table 2 shows the time costs of different sections. We can see that the average time spent for one convex hole is low, such that our proposed method is able to be used in real time. To validate that with sparse and noisy map points, our method can construct navigable space in real time and further facilitate local path planning for safe navigation. We conducted indoor experiments with our real robot. The indoor navigation experiment shows that the proposed convex hall growing method is effective and fast to construct free space in the presence of sparse and noisy maps. Therefore, the proposed approach contributes to a lightweight safe navigation framework which is essential to autonomous mobile vehicles, especially when other high-definition ranging sensors are not available. Thanks for watching, and let me know if you have any question.